Have you ever woken up in a room with no windows and no clock, and felt your body insist that it already knows what time it is? You didn't check anything. You didn't calculate anything. Some part of you just knew, or thought it knew, and it turned out to be close to right. That feeling is strange when you stop to notice it, because nothing in the room told you the answer. No sunlight crossed the wall, no sound marked the hour, and yet something inside you was still counting, still keeping a kind of time that has nothing to do with a phone screen or a wall clock. Where did that sense come from, and how far back does it go? Did the earliest humans, the ones who lived long before the first calendar was ever carved or the first clock was ever built, have any way of tracking days, seasons, and years at all? Or did they simply live inside an endless, undivided present, with no sense of dates, no sense of duration, nothing but hunger and light and dark? You are about to find out, and the answer will change the way you think about every time you have ever glanced at a clock without meaning to. Start with the assumption most people carry around without ever examining it, that timekeeping is a modern invention, something that arrived with writing, with civilization, with the first scribe pressing a stylus into wet clay to mark a tax season. That assumption feels reasonable. Calendars, after all, look like technology. They look like the kind of thing that requires cities, granaries, kings, and bureaucrats to keep everyone's planting schedule straight. It is easy to imagine that before all of that, humans simply drifted through an undifferentiated blur of days, waking when it was light and sleeping when it was dark, with no deeper structure to their sense of time. But that assumption turns out to be almost exactly backward. The truth is that the human body and the human mind were built for timekeeping millions of years before the first city existed, and they were built that way not as a luxury, not as an intellectual hobby, but as a matter of survival, so fundamental that the organisms who failed at it did not live long enough to pass on their genes. Timekeeping is not something civilization invented. Civilization only formalized something that was already ancient. To understand why, you have to go back further than you might expect, past humans entirely, into the deep evolutionary history of life on a rotating planet. Every organism that has ever lived on Earth has lived under the same relentless cycle. The planet spins, and every point on its surface swings from light into darkness and back again, once every roughly 24 hours, forever. This cycle is not a human invention. It predates humans by billions of years, and because it is so reliable, so mathematically consistent, evolution did something clever with it. Evolution built internal clocks into living cells themselves, clocks that run on a roughly daily cycle even when there is no external light to check against. Biologists call this a circadian rhythm, from the Latin circa, meaning around, and dies, meaning day. It is, quite literally, an internal sense of around a day that operates inside your cells right now, and it operated inside the cells of your most distant ancestors as well, long before anything resembling a modern human walked the earth. Here is where the first genuine question of this video opens up, and it is one worth sitting with for a moment. If this internal clock exists inside your cells without any outside help, does that mean your body would still know roughly what time it is even if you were completely cut off from daylight, from clocks, from any signal of the outside world at all? It seems almost too strange to be true, that your body could keep time all on its own, with nothing to check itself against. But this is exactly the kind of question science does not leave hanging forever, and there is a real experiment that answers it directly, one so extreme that almost nobody would volunteer for it today. In 1962, a French geologist named Michel Siffre descended into a cave system beneath the French-Italian Alps and stayed there, completely isolated from daylight, clocks, and calendars, for 2 months. He had no way of knowing what time it was on the surface. He ate when he was hungry and slept when he was tired, and every time he woke up or fell asleep, he called a research team on the surface to log the exact moment, without knowing what the actual surface time was. When Siffre finally emerged, blinking into daylight, he believed the date was somewhere in the middle of August. In reality, it was mid-September. His internal sense of time had drifted, but it had not collapsed. His body had kept counting roughly 1 day at a time for nearly 2 months underground, entirely without sunlight, entirely without any external cue at all, simply because his cells were running an ancient biological clock that did not require his conscious mind to check a calendar. That clock had been shaped by hundreds of millions of years of organisms living on a planet that spins once a day, And it does not switch off just because you happen to be sitting in the dark. This is not just a strange anecdote about one adventurous geologist either. Decades of follow-up research, including further isolation experiments conducted by Siffre himself later in his life, and by other chronobiologists working in caves, bunkers, and specially designed sealed laboratories, confirmed the same basic pattern again and again. Human volunteers isolated from all external time cues consistently settled into a sleep-wake cycle close to, but not exactly, 24 hours, usually drifting slightly longer, somewhere around 24.5 hours on average, before their sense of elapsed time gradually diverged from the actual calendar outside. The consistency of this drift across many different individuals and many different experiments told researchers something important. This was not random confusion or forgetfulness. It was a genuine internal oscillator, a biological mechanism running on its own schedule, only needing daylight to correct and fine-tune itself, rather than to function at all. The mechanism behind this was eventually traced down to the level of individual genes. In the 1970s and continuing through the following decades, researchers including Seymour Benzer and his student Ronald Konopka identified specific genes in fruit flies that, when mutated, disrupted the insect's normal daily activity rhythms. Decades later, the geneticists Jeffrey Hall, Michael Rosbash, and Michael Young extended this work dramatically, uncovering the precise molecular feedback loop involving proteins that build up over the course of a day and then break down overnight, that keeps cells oscillating on an approximately daily rhythm. Their research, which earned them the Nobel Prize in Physiology or Medicine in 2017, confirmed that this clock is not a metaphor. It is a literal biochemical mechanism, present in the cells of fruit flies, mice, and humans alike, inherited across an almost unimaginably long evolutionary lineage, stretching back long before anything resembling a human brain existed. This matters enormously for understanding ancient humans, because it means the very first form of timekeeping was never a technology at all. It was biology. Long before any human being consciously decided to track anything, their bodies were already tracking the day-night cycle automatically, adjusting hormones, body temperature, alertness, and hunger on a rhythm tuned to roughly 24 hours. Every early human who ever lived woke into a body that already had a rough sense of daily time built into it, whether they thought about it or not. The first clock humans ever had was not carved from bone or built from stone. It was already running inside them, inherited from ancestors going back long before anything you would call human existed at all. But biology only gets you the day. It does not by itself get you the week, the month, the season, or the year. Those longer units of time require something more than an internal clock ticking away in your cells. They require paying attention to the outside world, noticing patterns that repeat over longer stretches, and holding that pattern in memory long enough to use it again the next time it comes around. So the next question becomes, once humans had this built-in sense of the day, when did they start noticing and using longer cycles, and what was the very first longer cycle they are likely to have tracked? The answer very likely points to the moon, and it points to the moon for a reason that becomes obvious the moment you actually stop and look at it. The moon is the single most visible, most dramatic, most reliably repeating object in the night sky. It changes shape in a completely predictable sequence, growing from a thin crescent to a full bright disk and back down to nothing, over and over, roughly every 29.5 days. Unlike the stars, which barely seem to shift from one night to the next, the moon visibly transforms almost every single night, in a pattern any attentive observer could notice within a single cycle, and confirm within 2 or 3. For a species whose survival depended on paying extremely close attention to the natural world, the moon would have been almost impossible to ignore. And there is physical evidence, carved directly into bone, that suggests early humans were doing exactly this, tens of thousands of years before the first city, the first farm, or the first written word. Consider a small piece of baboon fibula, a leg bone, discovered in a rock shelter in the Lubombo Mountains on the border of South Africa and Eswatini. This object, now known as the Lubombo bone, is estimated to be somewhere around 43,000 years old, which places it well within the range of early modern humans living in southern Africa. The bone is covered in 29 deliberately carved notches, cut in a clear, consistent sequence. 29 notches. If that number sounds familiar, It should, because it sits remarkably close to the 29.5-day length of a lunar cycle. Some archaeologists who have studied the bone believe it may represent a tally of a lunar month, a physical record kept by scratching a mark into bone each time the moon completed some portion of its cycle, or perhaps each time a specific phase recurred. It is worth being honest here. This interpretation is not universally accepted. Some researchers argue the notches could just as easily represent a simple counting tool, unrelated to the moon at all, since humans count all kinds of things for all kinds of reasons, and a tally mark by itself does not announce its own purpose. But the number of notches so close to a lunar month, combined with how visually dominant the moon would have been in a world with no artificial light polluting the night sky, makes the lunar interpretation a serious and widely discussed possibility, not a fringe guess. There is a second object that pushes this story even further, and it comes from Central Africa, near the town of Ishango, on the border of the Democratic Republic of Congo and Uganda, close to the headwaters of the Nile. The Ishango bone, dated to roughly 20,000 years ago, is far more complex than the Lubombo bone. Instead of one simple row of notches, it has 3 separate columns, each containing groups of notches, arranged in specific clusters, rather than one uniform line. In one column, the notches appear in groups that include numbers like 11, 13, 17, and 19, and if you add pairs of these groups together, or examine how they cluster, you get patterns that some researchers have connected to lunar observation across multiple months, essentially a longer-running calendar rather than a single tally. The Belgian scientist Jean de Heinzelin, who first studied the bone in detail after its discovery, initially proposed it might represent a simple arithmetic exercise. But later researchers, including the anthropologist Alexander Marshak, who spent years examining ancient bone artifacts under magnification, argued that the groupings looked less like an accident and more like a structured lunar record, potentially tracking phases of the moon across roughly 6 or 7 consecutive lunar cycles. Marshak's broader argument, developed across decades studying artifacts like this one across Europe and Africa, was that early humans were engaged in what he called notational behavior, deliberately marking time in a symbolic, cumulative way, long before anyone had invented writing in the sense we use the word today. It is important to be careful and honest about what this evidence does and does not prove. Neither the Lubombo bone nor the Ishango bone comes with an instruction manual. Nobody left behind a note explaining exactly what these notches meant to the person who carved them. Archaeologists disagree, sometimes sharply, about how confident we should be in the lunar interpretation versus simpler explanations like basic tallying or counting objects, animals, or people. But even with that appropriate caution built in, the existence of these bones tells you something remarkable on its own. Tens of thousands of years before agriculture, before cities, before anything resembling written language, humans were already engaged in the act of marking time deliberately, cutting physical, permanent records into bone, rather than simply letting each day pass and vanish from memory. Whatever the exact purpose, this is timekeeping technology in its earliest possible form, an external memory device for tracking something that mattered enough to be worth carving into bone by hand. This raises the next question naturally. If the moon was the first thing humans tracked beyond a single day, why would tracking it have mattered so much in the first place? What was actually at stake for a small group of early humans, living by hunting and gathering, in knowing where they were in a lunar cycle? The answer connects directly to how early humans actually lived, and it is worth taking the time to really unpack this, because the stakes were not abstract. They were about survival in a very immediate physical sense. Early human groups, particularly before the invention of reliable artificial light, were significantly more vulnerable to predators and to the simple danger of moving around in total darkness during a new moon, when almost no natural light reaches the ground at night. A full moon, by contrast, provides enough illumination to travel, to hunt certain nocturnal or crepuscular animals more safely, and to see potential threats approaching from a distance. Knowing roughly where you stood in the lunar cycle could shape a very practical decision. Is tonight a good night to travel between camps, to hunt a specific type of prey, or to gather firewood a bit further from camp than usual? Or is tonight a night better spent close to the fire, because the coming darkness will be nearly absolute? Beyond immediate safety, there is a strong argument, supported by research into the behavior of many present-day hunter-gatherer societies, that lunar timing mattered for coordinating group activities across distances. If two bands of the same larger social network needed to meet at a particular location for a shared hunt, a trade exchange, or a seasonal gathering, and they had no way to send a message ahead, agreeing to meet at the next full moon, or 3 moons from now, provided a shared, externally verifiable countdown that both groups could track independently and still arrive at the same understanding. Anthropologists studying modern hunter-gatherer groups, including work among groups like the Hadza of Tanzania, have documented exactly this kind of lunar-based scheduling being used to coordinate movements and gatherings without any written calendar at all, simply by referencing how many moons had passed or how many moons remained. While you cannot directly prove that Ice Age humans used the moon in precisely this way, the logic is compelling, and it lines up closely with how contemporary hunter-gatherer societies, whose lifestyles in some ways echo ancient patterns, actually use lunar counting today. There is also a biological layer to this that deserves real attention rather than a passing mention. The human menstrual cycle averages close to 29 days, remarkably near the length of the lunar month, and some researchers have proposed that this overlap may have reinforced lunar awareness among early human groups, in a very direct, lived, bodily way, giving an additional independent reason for the moon's cycle to be something worth tracking and marking. This connection remains genuinely debated among scientists, and it would be misleading to present it as settled fact, but it adds another thread to why the moon, more than any other object in the sky, would have stood out as something worth counting. There is a further layer to this story worth exploring, because tracking the moon was never only about the moon itself. It was also about the deeper relationship between a human group and the land it depended on. In Aboriginal Australian cultures, some of the oldest continuously maintained cultural traditions on Earth, researchers studying oral tradition and what are often called songlines have documented detailed systems in which the timing of specific ceremonies, the movement between different territories, and the exploitation of specific seasonal foods were all bound together into a single interconnected calendar of sky, land, and story, passed down orally across many thousands of years, without ever needing to be written down. Anthropologists and astronomers, including researchers such as Dwayne Hamaker, who has studied Aboriginal astronomical knowledge extensively, have documented specific traditions in which the appearance, disappearance, and behavior of particular stars and constellations were used to signal the arrival of specific seasonal events, such as the emergence of certain edible grubs or the beginning of a particular fishing season. This shows that lunar and stellar tracking among ancient and traditional peoples was rarely an abstract exercise in astronomy for its own sake. It was almost always woven directly into the practical business of knowing when and where to find food, safety, and community. So by this point in the story, you can see a clear progression forming. The day was tracked automatically, biologically, without any conscious effort at all, inherited from a very long evolutionary history. The lunar month was tracked deliberately, observed with the eyes and recorded by hand, likely for reasons tied directly to safety, coordination, and possibly biology as well. But what about the next unit up, the one that determines whether it's cold or warm, whether particular plants are fruiting, whether particular animals are migrating? What about the season? If you have been enjoying learning how deep this goes, how far back the human habit of tracking time actually reaches, this is a good moment to tap like and subscribe, because there is a lot more of this ancient story left to uncover, and it only gets stranger from here. Tracking the seasons required something different from tracking the moon, because the sky itself does not announce the seasons nearly as obviously as it announces the lunar cycle. There is no giant glowing shape in the sky that visibly grows and shrinks along with winter and summer, the way the moon grows and shrinks from night to night. Instead, seasonal tracking for early humans almost certainly relied on paying extremely close attention to the natural world itself, treating the behavior of plants, animals, and the sun's position as a kind of living calendar written across the landscape rather than the sky. Consider what an early human hunter-gatherer actually needed to know in order to survive across an entire year in a temperate or seasonal environment. They needed to know roughly when specific plants would flower, fruit, or become toxic. They needed to know when specific herd animals would migrate through a particular valley, when fish would run up a particular river to spawn, when certain nuts would fall and become gatherable before rot or competing animals claimed them first. None of this required an abstract number for the year. It required close, repeated, generational observation of the local environment, passed down through direct experience and oral instruction from older members of the group to younger ones. This is sometimes called phenological knowledge, referring to the study and tracking of the timing of natural, recurring biological events. And there is strong evidence that hunter-gatherer societies around the world, both historically documented ones and, by extension, very likely ancient ones as well, relied on exactly this kind of environmental calendar to know where they stood in the year. Among the San peoples of southern Africa, whose way of life has been studied extensively by anthropologists, precisely because it offers a living window into forms of knowledge that stretch back an extraordinarily long time, researchers have documented detailed seasonal calendars built entirely around the flowering and fruiting of specific plants, the mating and birthing cycles of specific animals, and shifts in wind direction and temperature, with named seasons that do not map neatly onto the 4 seasons familiar from temperate Europe, but instead reflect the actual rhythm of the local Kalahari environment. This is a crucial point, because it shows that seasonal timekeeping was never a single universal system waiting to be discovered. It was, and still is, a deeply local form of knowledge, built patiently over generations by people paying extraordinarily close attention to the specific patch of Earth they depended on to survive. There is also the sun itself, which, while it does not change shape the way the moon does something else that is just as reliable and, if you know to look for it, just as visible. As the year progresses, the exact point on the horizon where the sun rises and sets shifts gradually, moving further north in one direction through part of the year, and further south through the other part, before reversing and repeating the cycle the following year. If you consistently watch the sunrise or sunset against a fixed landmark on the horizon, a particular mountain peak, a gap between hills, a distinctive rock formation, you can track the sun's slow drift with real precision, and you can use that drift to know roughly where you are in the solar year, entirely without any device more sophisticated than your own eyes and a memorable landmark. Before looking at the most famous example of this kind of solar architecture, it's worth pausing on one that predates it by well over 1,000 years, and that rarely gets the same attention. Deep in the Nubian desert of southern Egypt, near a site called Nabta Playa, archaeologists, including the American researcher Fred Wendorf, discovered a circular arrangement of small standing stones, dated to roughly 7,000 years ago, making it considerably older than Stonehenge. The stones at Nabta Playa are modest compared to the massive megaliths of Wiltshire, but their alignment is not modest at all. Certain stones within the circle line up with the position of the sunrise on the summer solstice, at a time when this region of the Sahara was not yet the desert it is today, but a semi-arid grassland that depended heavily on seasonal monsoon rains. For the cattle-herding people who built and used this site, knowing precisely when the solstice arrived, and by extension when the life-giving seasonal rains were likely to follow, would have been a matter of genuine survival, not idle curiosity. Wendorf and his colleagues argued that Nabta Playa represents one of the earliest known examples anywhere in the world of a monument built specifically to track the solar year, with architectural precision, predating Stonehenge by well over a millennium, and showing that this kind of ambitious, community-scale solar observation was not limited to any single region or culture. This brings the story to one of the most visually striking and famous pieces of evidence for ancient timekeeping anywhere on Earth, and it comes from a period long after the Lubombo and Ishango bones and after Nabta Playa, but still thousands of years before most people imagine organized timekeeping existing at all. In Wiltshire, England, around 5,000 years ago, Neolithic builders began constructing what would eventually become Stonehenge, an enormous circular arrangement of massive standing stones, some of them transported from many miles away, using nothing but human labor, rope, timber, and an extraordinary amount of coordinated effort. Stonehenge is famous today mostly as an ancient mystery, but one of its features is not mysterious at all once you understand what it does. The monument is aligned so that on the summer solstice, the longest day of the year, the sun rises directly over what is known as the heel stone, a specific standing stone positioned outside the main circle, and its light travels directly into the heart of the monument along a precise axis. On the winter solstice, the shortest day of the year, the alignment works in the opposite direction, with the sunset lining up along the same axis in reverse. This is not something that happens by accident. Building a structure with this level of solar precision requires years, likely decades or even generations, of careful, repeated observation of exactly where the sun rises and sets at different times of year, followed by an enormous, deliberate engineering effort to encode that observation permanently into stone. Archaeologists and archaeoastronomers, researchers who specifically study how ancient cultures tracked celestial events, including notable work by researchers such as Gerald Hawkins in the 1960s, and later more rigorously reassessed by others including Clive Ruggles, have concluded that Stonehenge's alignment with the solstices was almost certainly intentional, representing a monumental solar calendar built directly into the landscape. This means that by 5,000 years ago, and likely considerably earlier given how long it would take to develop this level of observational precision, at least some ancient human communities were not simply noticing the seasons through plants and animals. They were tracking the solar year with enough accuracy to construct permanent architecture around it. Stonehenge is not alone in this. In County Meath, Ireland, an enormous passage tomb called Newgrange, built even earlier than Stonehenge, around 5,200 years ago, contains a narrow opening above its main entrance called a roof box. For most of the year, the interior passage of Newgrange sits in complete darkness. But for a period of several mornings surrounding the winter solstice, and only during that narrow window, the rising sun aligns precisely with the roof box, sending a beam of light traveling down the entire 19-meter passage to illuminate the inner chamber at the heart of the monument. This alignment is so precise that it could only have been achieved through repeated, careful observation of the sunrise position across many years, followed by an enormously deliberate construction process designed specifically to capture that one narrow moment. Modern researchers who study the site, including work coordinated through Ireland's Office of Public Works, which conducts an annual lottery for the small number of people allowed to witness the solstice illumination in person, treat this alignment as one of the clearest examples anywhere in the ancient world of a structure built explicitly to mark the turning point of the solar year. Here is a genuine question worth pausing on. Why would people go to this much effort? Why build something this massive, this labor-intensive, simply to mark a single sunrise on a single day of the year? The answer connects back to something you may already sense intuitively. In a world without any written calendar, without any device that could reliably tell you where you stood in the year, the winter solstice, the shortest day, represented the turning point after which daylight would slowly begin to return and lengthen again. For agricultural or semi-agricultural communities dependent on knowing when to expect the return of longer days and the eventual return of planting season, marking that exact turning point with total certainty, rather than relying on rough guesswork, would have carried enormous practical and likely spiritual weight. A monument like Newgrange or Stonehenge does not just track time, it publicly, permanently declares the answer to one of the most important questions a community living close to the land could ask. Has winter truly turned the corner yet, or not? This takes the story to its next natural stage, the counterintuitive twist that reframes almost everything discussed so far. It would be easy to assume that this entire progression, from biological day to lunar month to solar year, represents a neat, tidy staircase of increasing sophistication, with each step building cleanly on the last, moving steadily toward the modern calendars used today. But the historical reality is messier and, in a way, more interesting than that. The moon and the sun do not divide time into neat, compatible units. A lunar month is approximately 29.5 days. A solar year is approximately 365.25 days. 12 lunar months add up to only about 354 days, roughly 11 days short of a full solar year. This mismatch, sometimes called the incommensurability of lunar and solar cycles, created a genuine, persistent problem for any ancient society trying to use both systems together, and it is a problem that ancient timekeepers spent thousands of years wrestling with, using solutions that varied dramatically from one culture to another. Some ancient calendar systems chose to track the moon and let the seasons drift relative to it, accepting that a given month name might eventually occur in a completely different season decades later. Other systems periodically inserted an extra leap month to resynchronize the lunar count with the solar year, a technique used, for example, in the ancient Babylonian calendar. and later refined mathematically by Babylonian astronomers who left behind cuneiform tablets, recording remarkably precise observations of lunar and planetary cycles centuries before the rise of Greek astronomy. This means that the sophisticated, mathematically reconciled calendars, familiar from later civilizations, were not a simple, natural evolution from earlier lunar tallying. They were the product of an ongoing, difficult negotiation between two natural cycles that simply do not divide evenly into one another. A negotiation that took thousands of years, involved multiple false starts, and was solved differently in different parts of the world at different times. Look at how differently separate ancient cultures handled this exact same mathematical headache, entirely independently of one another, and the scale of the problem becomes even clearer. Ancient Egyptian timekeepers eventually moved toward tracking the solar year directly, rather than reconciling it with the moon at all, partly because their entire agricultural life depended on the predictable annual flooding of the Nile, a purely solar seasonal event with no lunar component whatsoever. They noticed that the star Sirius would reappear on the eastern horizon just before dawn, after a period of invisibility, at almost exactly the same time each year that the Nile flood began, and used that stellar reappearance, known as a heliacal rising, as an anchor point for their calendar instead of relying on the moon. Meanwhile, in ancient China, astronomers developed a lunisolar system that inserted extra leap months on a recurring schedule to keep lunar months roughly aligned with the solar seasons, a system refined over many centuries and still visible today in the structure of the traditional Chinese calendar, which is why the Lunar New Year shifts around within a roughly one-month window relative to the fixed solar calendar used internationally. Ancient Mesoamerican civilizations took yet another approach entirely, running multiple calendars simultaneously, including both a 260-day ritual cycle and a separate 365-day solar cycle, tracking both in parallel and noting the much longer cycle of days it would take for both systems to realign with one another. A cycle of 52 years known to the Aztec and other Mesoamerican peoples as the calendar round. Each of these solutions arose independently, shaped by local astronomical observation, local agricultural needs, and local mathematical traditions, with no single correct answer ever emerging, only different cultures making different practical peace with the same fundamental mismatch between the moon's rhythm and the sun's rhythm. This adds a genuinely surprising layer to the story. Ancient timekeeping was not a single invention that steadily improved in a straight line. It was a patchwork of independent, imperfect solutions, developed by different groups in different regions, often without contact with one another, each wrestling with the same fundamental mismatch between the moon's rhythm and the sun's rhythm, and each arriving at their own particular compromise. The neat uniform calendar most people use today, a fixed number of days divided into 12 months with an occasional leap day, is itself the product of this long historical negotiation, refined and adjusted repeatedly, including the well-documented Julian and later Gregorian reforms that corrected accumulated drift. In the Roman calendar system many centuries after Stonehenge and Newgrange were already ancient monuments in their own right. Now bring this back to something you can actually feel today, in your own body, in your own daily life. Because this is where the ancient story stops being a piece of distant history and starts becoming a mirror, held up to your own experience. Remember Michel Siffre, isolated underground with no clock and no sunlight, whose body kept a rough internal count of days anyway. That same biological clock is running inside you at this exact moment. And researchers who study circadian biology, including decades of work following on from Siffre's early experiments and expanded by sleep scientists, studying what is sometimes called the human body's master clock, located in a small region of the brain called the suprachiasmatic nucleus, have shown that this internal rhythm continues to influence your alertness, your hunger, your mood, and your sleep timing, whether or not you ever consciously think about it. When you feel inexplicably tired at roughly the same time every evening, or find yourself waking up moments before an alarm goes off, you are experiencing the same ancient biological clock that once ran inside every early human, the same clock that gave Siffre a rough sense of passing days even underground in total isolation. And remember the moon-tracking notches on the Lubombo and Ishango bones, and consider how closely that instinct mirrors something almost everyone still does constantly today, almost without noticing, marking the passage of time in small, physical, repeatable units. Every time you make a check mark on a habit tracker, Every time you cross a day off a countdown calendar hanging on a wall, every time you notch a tally into a piece of paper while counting something manually, you are doing, in essence, the exact same thing that a human being was doing on that baboon fibula in the Lubombo Mountains more than 40,000 years ago, turning the abstract, invisible passage of time into something physical, countable, and permanent, something you can look at and know exactly how much has passed without having to trust memory alone. There is one more modern echo worth sitting with before returning to the original question, because it shows just how much tension still exists today between the ancient biological clock inside you and the artificial schedules layered on top of it. Researchers studying what is now commonly called social jet lag, including the chronobiologist Till Roenberg, have documented that most people in modern industrial societies live with a persistent mismatch between their internal biological clock and the external schedule imposed by work, school, and artificial lighting, a mismatch that produces something functionally similar to the jet lag felt after crossing time zones, except experienced continuously, week after week, simply from living out of sync with one's own natural rhythm. This research shows that the ancient tension between internal biological time and external practical time, the same tension that shaped how early humans balanced their built-in daily clock against the practical demands of hunting, gathering, and travel, has never actually gone away. It has simply changed shape, from deciding whether tonight is safe to travel under a full moon, to deciding whether to answer one more email before an alarm clock, tuned to a schedule your body never fully agreed to, forces you awake regardless of what your internal clock would have preferred. And remember Stonehenge, Newgrange, and Nabta Playa, built to capture one single, precise, meaningful moment each year, the turning point of the solar cycle, using nothing but patient observation and enormous collective effort. That same underlying need, the need to mark significant turning points in time, and to do so with ceremony, with gathering, with shared attention, has never disappeared. It shows up in modern celebrations of the new year, in solstice gatherings still held at Stonehenge today by thousands of visitors who travel specifically to watch the sunrise align with those ancient stones, and even in something as simple as a birthday, which is, at its core, nothing more than a personal solar calendar, marking one full return of the sun to roughly the same point in its yearly path, relative to the day you were born. So return now to the question that opened this entire story. Did ancient humans keep track of time in any way, across days, seasons, and years? The full answer, built from everything you have just learned, is that they tracked all three, and they did so far earlier and far more precisely than most people ever imagine. The day was never something they had to learn to track at all, because it was already built directly into their biology by hundreds of millions of years of evolutionary history. The same silent internal clock that let Michel Cifre count nearly 2 months underground without a single external cue. The month, marked by the visible, dramatic cycle of the moon, was tracked deliberately and physically, carved by hand into bone, tens of thousands of years ago, on artifacts like the Lubombo and Ishango bones, likely for reasons tied to safety, coordination between distant groups, and possibly the rhythms of the human body itself. And the year, the longest and least visually obvious cycle of all, was tracked through patient, generational observation of plants, animals, and the slow, creeping drift of the sunrise and sunset along the horizon, eventually encoded permanently into monumental architecture, at sites like Stonehenge and Newgrange, structures built with enough precision to capture a single sunrise on a single day, out of 365. None of this required writing. None of it required cities, kings, or bureaucracies. It required only close attention, careful memory, and a species whose survival depended on knowing, with real precision, exactly where it stood in the endless, repeating rhythm of days, moons, and years. The next time you wake up in an unfamiliar room with no clock in sight, and some quiet part of you still insists it already knows roughly what time it must be, you are not imagining a strange coincidence. You are feeling the same ancient rhythm that guided every human who ever carved a notch into bone to mark a passing moon, and every human who ever stood in the cold morning air, watching patiently for the sun to rise exactly where they knew, from long experience, it eventually would.